Welcome to our lesson on colligative properties in chemistry. These are special properties of solutions that depend only on the number of dissolved particles, not on their identity. Colligative properties are special characteristics of solutions that change based on how many solute particles are dissolved, not based on what those particles are. In other words, these properties depend on the concentration of solute particles in a solution. There are four main types of colligative properties. First, we have vapor pressure lowering. Second, boiling point elevation. Third, freezing point depression. And fourth, osmotic pressure. Each of these properties is affected by adding solute to a solvent, and the magnitude of the effect depends on how many particles are dissolved. Let's start with vapor pressure lowering. When a solute is added to a solvent, the vapor pressure of the solution decreases. In a pure solvent like water, molecules at the surface can escape as vapor. But when solute particles are added, they take up space at the surface, reducing the number of solvent molecules that can escape. This relationship is described by Raoult's law, which states that the vapor pressure of a solution is equal to the vapor pressure of the pure solvent multiplied by the mole fraction of the solvent in the solution. Next, let's look at boiling point elevation. When solute particles are added to a solvent, the boiling point of the solution increases. This happens because the vapor pressure is lowered, so the solution needs to be heated to a higher temperature to reach the external pressure and boil. The change in boiling point is directly proportional to the molar concentration of the solute, and we can calculate it using the formula delta T sub B equals K sub B times M times I, where delta T sub B is the boiling point elevation, K sub B is the ebullioscopic constant specific to the solvent, M is the molality of solution, and I is the Van Hoff factor, which accounts for dissociation of the solute. Now, let's discuss freezing point depression. When solute particles are added to a solvent, the freezing point of the solution decreases. The solute particles disrupt the formation of the crystalline structure of the solid solvent, making it more difficult for the solution to freeze. Similar to boiling point elevation, the change in freezing point is directly proportional to the molar concentration of the solute. We calculate it using the formula delta T sub F equals K sub F times M times I, where delta T sub F is the freezing point depression, K sub F is the cryoscopic constant specific to the solvent, M is the molality, and I is the Van Hoff factor. A common example is adding salt to ice to melt it in winter. The salt lowers the freezing point of water, so ice melts even when the temperature is below 0 degrees Celsius. The fourth colligative property is osmotic pressure. Osmotic pressure is the pressure that needs to be applied to a solution to prevent the flow of solvent molecules across a semipermeable membrane. When a solution and a solvent are separated by a semipermeable membrane, solvent molecules tend to flow from the pure solvent side to the solution side. The osmotic pressure, pi, can be calculated using the Van Hoff equation. Pi equals I times C times R times T, where I is the Van Hoff factor, C is the molar concentration, R is the gas constant, and T is the absolute temperature. Now, let's solve a numerical problem on freezing point depression. Question: calculate the freezing point of an aqueous solution containing 10 grams of glucose, C6H12O6, in 250 grams of water. The freezing point of pure water is 0 degrees Celsius, and the cryoscopic constant, K sub F, for water is 1.86 degrees Celsius per mole. First, let's identify the data. Mass of glucose is 10 grams. Mass of water is 250 grams. Molar mass of glucose, C6H12O6, is 180 grams per mole. K sub F for water is 1.86 degrees Celsius per mole. Step 1. Calculate the number of moles of glucose. Number of moles equals mass divided by molar mass. Number of moles equals 10 grams divided by 180 grams per mole, which gives us 0.0556 moles. Step 2. Calculate the molality of the solution. Molality equals moles of solute divided by kilograms of solvent. Molality equals 0.055. 6 moles divided by 0.25 kilograms, which gives us 0.2222 mole. Step 3. Calculate the freezing point depression using the formula delta T sub F equals K sub F times M times I. Glucose is a non-electrolyte, so I equals 1. Delta T sub F equals 1.86 degrees Celsius per mole times 0.2222 mole times 1, which gives us 0.413 degrees Celsius. Step 4. Determine the new freezing point. The freezing point of the solution equals the freezing point of pure water minus delta T sub F. The freezing point equals 0 degrees Celsius minus 0.413 degrees Celsius, which equals negative 0.413 degrees Celsius. So, the freezing point of the glucose solution is negative 0.413 degrees Celsius. An important concept in colligative properties is the Van Hoff factor, I. The Van Hoff factor accounts for the dissociation of solutes in solution. For non-electrolytes like glucose or sucrose, I equals 1 because they don't dissociate. For electrolytes like sodium chloride, which dissociates into 2 ions, I equals 2. For electrolytes like calcium chloride, which dissociates into 3 ions, I equals 3. The Van Hoff factor can be included in our formulas. Delta T sub F equals K sub F times M times I, and pi equals I times C times R times T. To summarize, the 4 colligative properties of solutions are 1. Vapor pressure lowering 2. Boiling point elevation 3. Freezing point depression 4. Osmotic pressure. These properties depend on the concentration of solute particles, not on their nature. The key formulas we learned are delta T sub B equals K sub B times M times I for boiling point elevation. Delta T sub F equals K sub F times M times I for freezing point depression. Pi equals I times C times R times T for osmotic pressure. These concepts have real-world applications in everyday life, from using salt to melt ice on roads, to antifreeze in car radiators, to explaining how plants absorb water through root cells. Thank you for watching this video on colligative properties.